All right, so in the last video, I gave you an example of a matrix A and its LU factorization. And so we're actually going to use this factorization to solve a system AX equals B. All right, so we talked about how we can change this problem into two smaller problems. That's exactly what we're going to do. So we are going to use the LU factorization of our A, and that's from the previous problem. This is the A we're talking about, to solve the system AX equals B, where B is -7, 5, 2. All right, so since we know that A equals LU from above, we can break this down into those two components I mentioned before. First, we are going to take LY equals B and solve for Y. All right, and we know how to do this. Set up an augmented matrix. All right, so this is my L. And set it equal to B. All right, and then when we go through the process of row reducing it, I'm going to go ahead and just give us the answer. Putting in RREF. All right, so down the columns, I have 1, 0, 0, 0, 1, 0, 0, 0, 1. -7, -2, 6. All right, so now we have solved for Y, right? So Y is -7, -2, 6. Second step, now that we know what Y is, we are going to look at UX equals Y and solve for X, which is the solution of our linear system. All right, so we're going to take our matrix U down the columns if you don't have it in front of you. 3, 0, 0, -7, -2, 0, -2, -1, -1, -7, so set it equal to here, -2, 6. And we're going to row reduce. All right, down the columns, I have the identity. And I get 3, 4, -6. So I have now solved for X. All right, and so the nice thing about most of the problems in our class is we can always check, right? We can check that AX equals B by a quick multiplication. All right, so we've solved this system, but we skipped an important part. How did we know that this was the LU factorization? So let's talk about how do we figure that out. So I have a question for us. How do we find the LU factorization of A if it exists, because it may not? All right, so we're actually going to use our elementary matrices that we mentioned back in the matrix inverses section. All right, so here's what we're going to do. We are going to assume that we can take A and row reduce it into U. And here's exactly what we're going to do. Remember, U is an upper triangular matrix, which means it's an REF. So what we're going to do is row reduce A into REF. And that result is going to give us U. And the way we're going to do it is very, very particular. All right, the way we're going to row reduce it is only with one type of row operation. So we're going to do this using only, this is the only one, row replacements. Meaning updating Ri by multiplying some scalar times Rj and adding it to Ri. This is the only thing we're going to do. No swaps allowed. Also, there's no scaling allowed. There's only one type allowed when we're doing LU factorization. Okay, so what did we just say here? We just assume that A can be row reduced to be U using only this type. So that means that there's some sequence of elementary matrices. So like EP, EP minus 1, all the way to E1 times A, that will give us U. All right, so let's talk about what we're actually doing here and what these elementary matrices will actually look like. All right, so like I mentioned, we're only doing one kind of row operation, so it's only going to be one kind of elementary matrix. All right, so the kind of row operation we're doing is updating Ri by doing K times Rj plus Ri. What does that look like? Well, that is going to be an elementary matrix. Just kind of sketch it out here. So if it's an elementary matrix, we know it's going to look like the identity, but something has been changed, right? So we're going to have ones down the diagonal. Pretend like that's perfect. All right. And let's say that this is the ith row that we're updating. And let's say that this is the jth column. Corresponds with the row that we're scaling. All right, so when we take the identity and do this, we're just going to put the scale thing right here, the K. So what will this matrix look like, this elementary matrix? Zeros down the diagonal, sorry, ones down the diagonal, a K right here, and then zeros everywhere else. I'm gonna put a 0 here. That's what it's gonna look like. And so notice how stuff is in the bottom. So that tells us that when we do multiply these elementary matrices, we're gonna get a lower triangular thing, okay? So, if all of these elementary matrices multiplied by A gives us U, then what if we move them to the other side by taking the inverse? That means that A is going to be E1 to EP inverse times U. And this is L, our lower triangular matrix. All right, so in the next video we'll do an example of finding the LU factorization.